So, if you break your arm, an X-ray just shows a jagged white line, right?
Right. It's very binary.
Exactly. Broken or not broken. It's super clean. But what happens when an animal's DNA is just so intensely engineered by humans that their entire body becomes this, like, diagnostic gray area?
Yeah, that is a profound question, and it's exactly what we're tackling today.
Welcome to the Deep Dive. Today we are taking you on an exploration of the unintended physiological consequences of intense selective breeding in companion animals. And we've got a really fascinating stack of sources in front of us.
We really do.
Yeah, we're pulling from canine esophageal disorders, equine emergency medicine, a highly specific biomechanical study on horse hearts, and the incredibly strict breeding regulations of the Frisian horse.
It's a lot to cover, but it's a brilliant look at how modern veterinary science is essentially having to step in to save these highly specialized animals from their own genetic blueprints, you know?
Right. And our mission for you today is to really connect the dots here. From a tiny toy dog's throat to a majestic medieval warhorse's heart, and tying it all back to a genetic bottleneck from 1913, I am so excited to dive into this.
Me too. And to truly understand these complex creatures, I mean, we really have to look at the mechanical realities of how their bodies function, or in a lot of cases, fail to function under the hood.
Right, the mechanics. And to grasp the systemic failures we see in these breeds, we first have to understand the baseline mechanics of a crucial everyday function: swallowing.
Which sounds so simple.
Yeah, it sounds like a totally passive action.
Yeah.
But it's actually this highly coordinated four-stage process. You have the oral preparatory phase, the oral phase, the pharyngeal phase, and the esophageal phase.
And the physics of that entire process are just incredibly demanding. I mean, you're asking a sequence of muscles to move a solid mass of food safely past the respiratory airway and then down a long tube, often fighting directly against gravity.
Oh, wow, right.
And when you selectively breed for certain anatomical shapes, the plumbing can and does fail at very specific, predictable points. Take golden retrievers, for example.
Okay, what happens with them?
Well, they're predisposed to pharyngeal weakness. So the muscles in the back of the throat simply lack the structural strength to propel the food backward.
Ah, I see. And then you have Cocker Spaniels who develop what the sources call cricopharyngeal dysphagia.
Exactly.
And miniature dachshunds, they get a cricopharyngeal bar, which is essentially this localized hypertrophy, like a thickening of the muscle that physically obstructs the throat.
Right. And we also see major upper gastrointestinal issues driven purely by respiratory anatomy. Brachycephalic dogs, like French bulldogs, they have staggering rates of gastroesophageal reflux disease, or GERD.
I imagine this has something to do with their smushed faces, right? Like their restricted breathing.
Oh, absolutely. It's the direct mechanical cause.
Wait, really? How does that work?
Well, when you compress the nasal airway of a French bulldog, every time they try to take a normal breath, they're pulling against an obstruction. So this creates massive negative intrathoracic pressure.
Oh, man. So they're essentially turning their own chest cavity into a vacuum.
Yes, exactly. And that pressure difference literally sucks stomach acid backward right up into the esophagus.
That sounds miserable. And diagnosing exactly where and how these plumbing systems are failing requires some intense technology, right?
Right,
Because you're dealing with living, moving parts inside a tiny animal.
It's very complex. Veterinarians use videofluoroscopic swallow studies.
That's the one with the barium.
Yeah. They mix the dog's food with barium, which acts as a radiopaque contrast agent, and then they can literally watch the swallow happen in real time on a continuous X-ray video.
That's wild. They also use the Bravo pH monitoring system. I was reading about this in the sources. It's this brilliant piece of technology where a catheter-free capsule is temporarily attached directly to the lining of the esophagus.
It is brilliant. It continuously measures the acid reflux levels over several days, giving veterinarians a comprehensive, dynamic picture of the dog's baseline physiology. And it does this outside of the stressful clinic environment, which is key.
Okay, let's unpack this. If we look at cricopharyngeal achalasia, like what we see in those dachshunds, I was trying to visualize the actual mechanism. It's often described in the literature like a stubborn bouncer at a nightclub.
That's a great analogy.
Yeah, so the upper esophageal sphincter is the bouncer, and the food represents the VIPs trying to get into the club being the stomach. But the bouncer just straight up refuses to open the door.
What's fascinating here is to take that analogy a step further into the neurology of what's actually happening. It's not just that the bouncer is stubborn.
Right.
It's that the bouncer's earpiece is broken. Yeah. The neurological signal that's supposed to tell that sphincter muscle to relax at the exact fraction of a second the food arrives, it's just getting lost. The muscle remains locked in a state of rigid tension.
And so treating these issues across entirely different species relies on artificially manipulating that exact muscle tone. Like in dogs, vets might administer a drug like sildenafil, which acts on the cellular receptors, to just force that lower esophageal sphincter to relax.
Or they might use a drug like cisapride to artificially enhance the motility, like the muscular squeezing action of the gut.
But the way we manage that muscular tension changes drastically depending on the species we're dealing with, doesn't it?
Oh, entirely. If we look at horses, an esophageal obstruction is commonly referred to as choke.
And the average age for a horse to develop choke is around 10.5 years old, according to the data.
Right, which is where the diagnostic and treatment protocols completely diverge from canine medicine.
Yeah, because we just talked about how vets use barium to diagnose swallowing issues in dogs. But if a vet gives barium to a choking horse, it's a catastrophic, often fatal mistake.
A massively fatal mistake, yes. A choking horse is highly prone to aspirating whatever's in their throat directly down their trachea.
And if barium is inhaled,
If it's inhaled, it causes fatal barium pneumonitis. The lungs just react violently to the heavy metal compound, essentially destroying the respiratory tissue.
oh, that is terrifying. So instead, to deal with the metaphorical bouncer in a horse's throat, veterinarians rely heavily on alpha-2 agonists, like xylazine or ditomidine.
Exactly. These are heavy sedatives that profoundly relax the skeletal muscle of the throat and suppress the central nervous system.
So that allows the vet to safely pass a nasogastric tube down the nose into the esophagus and just flush the obstruction out with a lavage.
Yeah. Chemical software like xylazine works incredibly well if the muscle is just having a temporary spasm or if there's a localized acute blockage. But, what happens if the actual hardware, the physical tissue of the esophagus itself, is fundamentally defective from birth?
And that brings us to the core narrative of our deep dive today. We're looking at a specific animal where esophageal failure isn't just an isolated plumbing incident. It's a symptom of a much larger systemic genetic crisis, the Friesian horse.
The Friesian is just one of the most visually iconic breeds in the world. I mean, there are those majestic jet black horses with the thick flowing manes and heavy feathering on their lower legs. You see them in basically every medieval fantasy film.
But that striking uniformity comes with a profound biological cost. And it traces back to a massive genetic bottleneck. The historical numbers in the research are just staggering.
They really are.
In 1913, the entire global population of registered breeding Friesian stallions dropped to exactly 3.
Just 3 horses?
Yeah, just 3 horses carrying the genetic blueprint for the entire future of the breed.
Which means every single purebred Friesian alive today traces its lineage back to that incredibly tiny restricted gene pool.
And this established an intense inbreeding coefficient. Right now, it sits between 16% and 25.5% across the breed. And mathematically, that coefficient is fundamentally increasing by 1.5% every single generation.
And when you shrink a genetic pool to just 3 primary books of DNA, you aren't just passing down those beautiful black coats. You are forcibly magnifying every single hidden typo in their genetic code.
Right. The sources detail how these rare recessive mutations suddenly became breed-wide epidemics. We're talking about dwarfism, where the skeletal limbs are severely stunted while the head and torso grow to a normal size.
And hydrocephalus, which is a fatal accumulation of cerebrospinal fluid in the brain that causes catastrophic pressure.
Oh, and dystichiasis, that painful condition where abnormal stiff eyelashes grow inward and constantly scrape the surface of the eye.
Yeah, it's brutal. Those single gene mutations are devastating. But the most complex and systemic challenge the Friesian faces is something researchers have labeled the connective tissue hypothesis.
This was heavily detailed in the research, and I found it fascinating. Friesians consistently show elevated levels of pyridinoline cross-links in their urine. So to translate the biochemistry for you all, pyridinoline cross-links are essentially chemical markers that get flushed out of the body when collagen is breaking down.
Right, so their presence in high numbers indicates rapid abnormal collagen degradation. The horse's body is breaking down its own connective tissue at an accelerated rate.
And collagen is quite literally the biological glue holding the mammalian body together, right?
Exactly. It provides the tensile strength and elasticity for skin, tendons, ligaments, and internal organs. And because of this systemic weakness, Frisians experience a 54% rate of retained placenta after giving birth.
54%.
Yeah, because the collagen matrix required for the uterus to properly expel the tissue is compromised, and they suffer from widespread tendon and ligament laxity. And most crucially for our discussion, they develop a severe condition called megaesophagus.
Right. Megaesophagus is this chronic, paralyzing dilation of the esophagus. But this tripped me up during the research, actually.
Oh, yeah.
Yeah, if this is a systemic connective tissue issue, like if the collagen all over their body is degrading, why does it show up so prominently and catastrophically as a paralyzed throat?
It really comes down to the sheer mechanical demand placed on the equine esophagus. Think about it. A horse's neck is incredibly long, and they often swallow while their head is raised.
Oh, true.
So the esophagus relies on an intricate, highly coordinated matrix of muscle woven with collagen to grip a heavy bolus of chewed hay and push it down, often fighting gravity. So when that collagen matrix degrades, the esophageal pipes lose their structural integrity and elasticity. They just permanently dilate and stretch out.
Okay, so if you're trying to picture this, imagine trying to forcefully push a heavy volume of water through a totally flaccid balloon instead of a rigid rubber hose.
Yes, perfect visual.
The muscular squeezing action, the peristaltic wave, it just dissipates into the stretched out baggy tissue. The food has nowhere to go, so it just sits there, leading to chronic, repeating episodes of choke.
And because the connective tissue is fundamentally failing on a cellular level, there's no medical cure. You cannot surgically go in and tighten the entire length of a 1,500-pound horse's esophagus.
So the management of this disease becomes entirely mechanical and lifestyle-based. Like in dogs diagnosed with megaesophagus, owners often use something called a Bailey chair.
Right, I've seen those.
Yeah, it's essentially this custom-built high chair that forces the dog to sit completely upright on their hind legs while they eat. The owner feeds them from above, entirely bypassing the need for esophageal muscles and just letting gravity pull the food directly into the stomach.
But you cannot put a Frisian in a Bailey chair.
No, you absolutely cannot.
So the daily management falls squarely onto the shoulders of the owners and barn managers. They have to, completely abandon dry hay and normal grains. They must transition the horse to highly watered-down, soupy slurries.
And crucially, they have to feed these slurries at chest height or higher so gravity can assist the swallow.
Think about the intense coordination that requires. Because a megaesophagus horse cannot safely eat a massive meal all at once without the food backing up into their throat, this slurry has to be divided and fed 3 to 4 times a day.
Oh, man. And if you're boarding a horse at a commercial stable, that completely disrupts normal operational routines.
Totally. And in the winter, you can't leave a watery slurry in a normal feed bucket because it will freeze solid.
Right. So you have to install heated buckets and ensure constant, vigilant monitoring for aspiration pneumonia, which is a constant threat if the horse accidentally inhales any of that regurgitated fluid.
The dedication required from these owners is just staggering. But managing a faulty digestive tract with elevated feed buckets only goes so far. What happens when that exact same tissue weakness strikes a part of the body you cannot manage from the outside?
You're talking about the cardiovascular system.
I am.
Because the other fatal consequence tied to this connective tissue hypothesis is aortic rupture. Specifically, the Frisians suffer catastrophic tearing at a spot called the ligamentum arteriosum.
Right. The ligamentum arteriosum is a small band of tissue that essentially anchors the aorta near the heart. Researchers at Ghent University conducted a really fascinating, highly specific biomechanical study to understand why this was happening.
They wanted to test the actual physical tensile strength of these aortas. So they took tissue samples from Frisians affected by aortic rupture, non-affected Frisians, and warm blood horses, which serve as a genetic control since they're an entirely different breed.
And they mapped out the aorta and tested the tissue at the ligamentum arteriosum, which they labeled LA, the mid-thoracic area, labeled T1, and the distal area further down, labeled T2.
And they found that the distal aorta T2 is structurally much stiffer. It contains about 31% collagen compared to just 17% in the proximal LA area near the heart.
They also measured the failure stress of the tissue, which is essentially a metric of how much mechanical pressure the tissue can endure before physically tearing apart, and that's measured in megapascals.
Right. And the distal T2 region had a failure stress of 0.73 megapascals versus just 0.22 megapascals for the LA region.
So it's much weaker near the heart.
Exactly. If you're trying to picture this failure stress difference, imagine stretching a thick, brand new rubber band versus one that's been sitting in the sun and is starting to dry rot. It perfectly explains why the ruptures consistently happen at that weaker proximal LA area.
But the core finding of the Ghent University study was something literally no one anticipated.
Right.
Going into this, operating under the connective tissue hypothesis, one would assume the Frisian aorta would test significantly weaker than the warm blood aorta.
Here's where it gets really interesting. I was fully expecting the data to show the Frisian tissue behaving like wet paper under pressure. But the twist in the research is that they found zero significant biomechanical or biochemical differences between the Frisians and the warm bloods.
Zero.
In a static post-mortem pull test, the Frisian aortic tissue was just as strong and contained similar collagen properties as the healthy warm blood tissue.
This raises an important question. If the tissue itself isn't structurally weaker on the testing table, why are the Frisians the ones spontaneously dying from aortic ruptures?
Yeah, that is exactly the question the researchers had to confront.
And their conclusion points toward a dynamic failure rather than a static one. The ruptures might be caused by abnormal hemodynamic changes, meaning the specific pulsing forces of the blood flow inside the living horse, or chronic repetitive in vivo injury.
Oh, I see.
Yeah, a simple piece of laboratory machinery pulling a dead tissue sample apart in a straight line simply cannot capture the complex physics of a beating heart. It's not just about how strong the rubber band is, it's about how that rubber band is being violently plucked and twisted thousands of times a day inside the living animal.
Wow. So veterinary medicine cannot surgically fix a paralyzed megaesophagus, and a postmortem stretch test cannot fully isolate the mechanics of an aortic rupture.
No.
Which means we can't simply treat our way out of this crisis in the clinic. The only viable solution is to rewrite the future of the breed entirely. We have to stop the diseases at the genetic source.
And that monumental task falls to the registries. You have the KFPS, which is the Royal Frisian Horse Stud Book based in the Netherlands, and FINA, the Frisian Horse Association of North America.
And these organizations aren't just administrative clubs. They hold total global authority over the breed standard, and they are playing a very high-stakes game of genetic chess to ensure the Frisian survival.
They manage this through incredibly strict registry tiers. You have the main book, which is exclusively for approved purebreds, and then B Book 1 and B Book 2 for horses with unapproved sires.
But there is a pathway built into the system where B-book lines can slowly upgrade their status over several generations if they are consistently bred to approved stallions.
And the evaluation process for these adult horses is intense. I mean, they use linear score sheets where 60% of the horse's total score is based entirely on the biomechanics of their movement and 40% on their physical conformation.
And the top-performing horses earn elite predicates. You have the star predicate, awarded to the top 25 to 30% of horses, then crown. And the highest conformation standard is the model predicate.
But they don't just hand out model status to a pretty horse.
No, they demand proof of physical and genetic resilience. To be a model mare, she has to be at least 7 years old, stand a minimum of 1.6 meters tall, score an 8.0 or higher on her physical inspection, and she must have successfully nursed a foal.
Which is huge. They require that to prove her internal reproductive collagen and fertility haven't been hopelessly compromised by the inbreeding.
There's also the sport elite predicate, which is purely performance-based. It requires achieving 5 scores of 60% or higher at the pre-St. George's level in dressage.
And for those unfamiliar with the sport, pre-St. George's is a highly advanced level of competition. It demands extreme muscular collection, balance, and joint strength from the horse.
So earning that predicate proves the horse's skeletal and muscular systems are fundamentally sound under intense athletic pressure.
Exactly. But the real front line of this battle for the breed's future is genomic management. Every single approved stallion must submit to a comprehensive DNA test.
But here is where the math becomes incredibly delicate, right? Because there are only about 100 approved breeding stallions globally.
Right.
If the registry looked at the DNA results and decided to completely ban every single stallion that carried a recessive mutation for dwarfism or hydrocephalus, the gene pool would completely collapse. There simply wouldn't be enough genetic diversity left to sustain the breed.
Yeah, so counterintuitively, the registry actually allows carriers of these fatal genetic diseases to breed.
So what does this all mean? Well, I like to think of their strategy like the computer game Minesweeper.
Oh, that's good.
Yeah, carrier breeding isn't about ignoring the genetic bombs hidden in the field. It's about aggressively mapping exactly where they are. Because these diseases are recessive, it requires 2 copies of the mutated gene, one from the sire and one from the dam, to produce a sick foal.
Exactly. If you know a stallion is a carrier for dwarfism, You strictly mandate that he can only be mated to a tested non-carrier mare.
Right.
That ensures a 0% chance of producing a foal afflicted with the disease, while allowing the breeder to safely navigate the minefield and preserve the tiny fraction of healthy genetic real estate that stallion still possesses.
If we connect this to the bigger picture, balancing a 16% inbreeding coefficient requires treating every single breeding decision like a mathematical science. Breeders rely heavily on calculated kinship percentages, striving to keep a new foal's inbreeding coefficient strictly below 5%.
But simultaneously, they're using modern sports science to respect the physical living limits of the animal standing right in front of them.
Oh yes, the sports science study.
We have a brilliant example of that sports science fundamentally changing the industry. To become an approved breeding stallion, young horses undergo a grueling 70-day central examination where their stamina and trainability are rigorously tested.
But when researchers analyzed this process in 2020, the physiological markers showed that the young stallions were actually overtraining. Their bodies were breaking down under the stress.
Yeah, the researchers analyzed the plasma lactate levels, which indicate muscle fatigue, and their heart rate recovery times. They realized that more training was actually destroying the horse's fitness.
So they completely rewrote the protocol.
They dropped the training frequency from 4.4 days a week down to 3.8 days. They capped the strenuous riding sessions at exactly 24 minutes, and they mandated that trainers alternate high-intensity workdays with active rest, like paddock turnout or light lunging.
And the physiological result was undeniable. By working the horses less and respecting their cellular need for recovery, their measurable physical fitness actually increased. The lactate levels dropped, and the heart rate stabilized faster.
It's a perfect encapsulation of the shift we're seeing across the board. We are finally using data and science to step back and let the biology thrive, rather than forcing the animal's body to blindly conform to human expectations or, arbitrary schedules.
Think about the massive scope of the ground we've covered today.
Yeah.
I mean, we started by looking at microscopic, catheter-free Bravo pH capsules, precisely measuring acid reflux in the structurally compromised airways of French bulldogs.
And then we explored the painstakingly intense daily routine of a barn manager mixing soupy slurries and carrying heated buckets in the freezing winter just to keep a megaesophagus horse nourished against gravity.
And we ended up examining the complex mathematical genetic chess game played by Frisian registries, all attempting to outrun the catastrophic shadow of a population bottleneck from 1913.
It really highlights just how deeply our human choices, our desire for a certain look, a certain coat color, or a certain size, have fundamentally shaped the very cellular structure of these animals, for better or worse.
It really does. And I want to leave you with a final thought to mull over today. We are currently utilizing unbelievable cutting-edge technologies, comprehensive DNA sequencing, high-resolution esophageal manometry, even magnetic sphincter implants in dogs, to surgically and genetically correct the physiological flaws that human selective breeding created in the first place.
Yeah, it's wild when you step back and think about it.
Right. So at what point does preserving a pure breed become more about our mastery of human engineering than a celebration of nature? And looking to the horizon, could we eventually use these exact same powerful genomic tools, not just to carefully step around disease, but to actively engineer the lost wild resilience back into these animals?
That's a great question.
Can we ever give them back the clean binary precision of the simple X-ray, where the plumbing just works? Something to think about. Until next time, stay curious.